So today I am going to discuss computational complexity for various types of problems. And as I defined in the previous lectures, there are various types of problems, decision problems, um, evaluation problems, relativized problems, etc. And we have to have a language which can do the counting. For decision problems, it is particularly simple because the problems are phrased in terms of integers. So you can literally count how much is the size of the data, how many steps you are going to take, what is the precision of the answer, etc. And they are all integers, so you can say that this is better than that, no problem. And so there is a standard notation which has been constructed for dealing with all these situations. And that is something which computer scientists used frequently, and it gives what is known as a asymptotic behavior of various quantities, and best is to just write those things down one by one. So there is a notation for upper bound which goes by the label capital O of some argument n, and it means that some functions is this. That means that f is less than or equal to some constant times n, for the asymptotic case where n is going to infinity. And you can put any function over here. Okay, I put n, but it can be e raised to n, so then this will be e raised to n, doesn't matter, but it's basically an upper bound which is denoted by this symbol, and there are variations which, well, I will illustrate for one of them, that instead of capital O you use small o, then f is strictly less than n instead of having an equal to sign also. So all stuff like this exists. There are many other variations you will find in the literature, something called O tilde, which is allows certain kind of corrections on top of this function, typically logarithmic. There is O star, which says you have ignored something, etc. But we don't have to worry about those stuff for this simple purpose of complexity which we're going to deal with. Okay, so there is this upper bound. Then there is a lower bound, which is denoted by this letter Greek capital omega, and which means that f is lower bounded. And then there is a exact scaling, which also occurs, and it is denoted by this Greek letter capital theta, which means that f is equal to some constant times n. All cases where n goes to infinity, the limit is kind of understood. So this is just a notation, and what we have done is two things. One is consider the limit of large value of the arguments. In case of problems, it will be the size of the input data in a certain sense. And the other thing is, you're not bothered about what that constant is. Now in practice, when you are trying to measure the efficiency of certain algorithm, it matters whether the constant is 1 or it is 100 or it is 1 over 100, whatever it is. It does a lot of what you call practical analysis when you want to run it on a computer. I mean, something can be impractical just because that constant is large. And that is something which at this particular stage ignored. But I should point it out that in practice, the value of the constant matters, and also both things are going to be true, so you don't take the limit and going to infinity. You want to actually calculate when n is 1000. How does the algorithm work? Okay, so those are the practical criteria, but this analysis kind of puts it away. We are not going to worry too much about it. We'll worry about when you actually come to the implementation of the problem. So this is one part which you need to get familiar with. Other things are various techniques. One of them is called reduction. Reduction specifies that one problem can be converted to another problem. And if I then solve the second problem, I will have an answer to the first problem. Okay. So it's very useful in many proofs, because if you show a certain kind of reduction, then you don't have to solve all possible problems, but just show that all variety of problems can be reduced to this particular problem, and then just solve that single problem. So that technique is called reduction, and the effort of reduction can also go in all these different counting. How much work I have to do to reduce one problem to another, well, that can be counted. And we will see examples of this kind of reductions in some of the complexity description that I am going to give. So Then there is a technique which I can call by this word negation. So these are the kind of problems where the emphasis is not solving it by converting to another problem, but instead saying that you cannot solve this. And it's a kind of a simple thing once you understand the logic, but it is something worth understanding at least once. So, to give an example, suppose I have a bunch of binary strings, a whole list of them. And then I ask you, find a string which is not in this list. How do I do it? Well, I can guess a random string and go on checking whether it is in that list or not. It doesn't work very well because how many strings you are going to check? If there are n bits, then there will be 2 to the power n strings, and you will have to keep on randomly sampling from that. No good. So the clever way to solve the problem, and actually it is the most efficient way, take the first string and define the new string which is having the first digit or first bit opposite to what is in the first string. Then the second digit is defined as opposite to what is there in the second string. The third bit is defined as opposite to what is there in the third string. And you go down the list, at the end you will have a string which is not contained in any of the previous one, because at least one digit is missing, or rather wrong. So that's the end of the story. You scan it once and you have the answer. No random guessing, nothing involved. And the peculiarity is that this works for list of arbitrary lengths. Doesn't matter how long you want to make the list. It works. So this is the construction of negation. It's very useful for denying certain results, basically. So and indirectly, I have given an example of this in the previous lecture, which is the halting problem. It's connected. It says you construct all this machine, something or the other. One instance, it will not work. That is good enough. And that is also a kind of useful techniques. And then you will have to look at certain aspects of logic where, well, binary variables can easily be mapped to true or false. And there are a whole lot of rules of logic and basically implication. That if I am given certain statement, something else will follow or not follow. That is the meaning of implication. And one thing which is worth remembering, that if something is true, it cannot imply something that is false. Okay, that will be contradictory. But the other way around is okay. You can arrive at the correct result by wrong arguments. Probably you are familiar with this in going through lots of exams. You found the answer. How you arrived at it may not be right. And that is something worth remembering. It will appear in the construction of logical algorithms, or, well, once you map true and false to 0 and 1, it's a binary structure as well. So this is just to give a quick summary of some important ideas. And now I can go to the actual labels of complexity classes, which are used frequently. Actually, it is a huge collection of symbols which you will find if you look at the website created by Scott Aronson. He just calls it a zoo, because there are so many things, and if you try to go through it, it has to be broken through alphabetically like a dictionary, because there are so many of them, and you get lost. So I am just going to use a few important ones which are the situations that we will deal with, and there is a hierarchy. Which says that some problem is simpler than some other problem. Okay. So the important hierarchy is given by this sort of labels. And I have to give a definition of each one of them. So what is P? It is a set of decision problems that can be solved with polynomial resources. How are you going to count this polynomial? Well, in this type of notation. Okay, whatever this thing comes, this function has to be polynomial. So best thing is to give very well-known example. So the addition of n bits is order n. You have to, well, at every bit you have to add 2 numbers, and if there is a carry, you take it into the next one, add that again, etc., etc. And how many steps you take? Well, it is n steps, and if there is a carry, then you have to do a little bit extra work, so it might become 2n, but fine. 2 or 1 doesn't really matter much, that is dumped out in the constant, and what remains is just order n. What about multiplication? Well, what do you do? In multiplication, the primary school method is take the number, multiply by the first digit, write it down. Then the second bit, write it down, but shift it by one place. Then multiply the third one, shift it by thing, etc., etc. And have to use the multiplication table for writing each row. Then you will get these a whole bunch of rows, and then you add them up. So now if you count the effort, it is of the order n square, because each digit you multiply, your one bit here, multiply the whole string, it is order n, and then you have to do whole calculation of adding all of those things together and additions of these rows, another factor of n, it becomes order n square. You can find better method incidentally for doing that, but this is the simplest thing which we all learned in primary school. Incidentally, in the binary arithmetic, this is much simpler because the multiplication table disappears. What you are doing is multiply by 0 or 1. Multiplication of 0, you don't have to write that row at all. Multiplication of 1 is just copy the whole thing. There is no multiplication table involved at all. So it's just a shift and copy n bits one after the other, and then add all of them together with order n square. If there is a carry bit, there might be some proportionality in front, but we don't worry about it. So these are the problems which can be called polynomial, because this function is a polynomial. Okay. What is this stuff? It is different than not polynomial. Okay, don't interpret it as not polynomial. It's not that. There is an extra word inside it. It's a non-deterministic polynomial. What does non-deterministic mean? That in trying to construct the algorithm, there are branches. Like if this, then do something else, do something else. There are branches. And depending on how many branches are there, the possibilities can rapidly grow. Okay. So this one is a single branch. Okay, there is no multiple branching involved in this polynomial problems, but in non-deterministic polynomial, there are branches which occur. What does a polynomial then mean? That if we are given the answer, the verification is polynomial. So this is a branching structure with verification is polynomial. Why this verification can be easy? Because it will go through the branches in the reverse order. Given the answer, you want to check whether it's correct or not, you have to go up the branch, and the reverse process is just number of steps. The branching doesn't matter. And again, a simple example is factoring a number. Again, whatever kind of stuff we played with in school. Well, if you're given a large number, how do you find the factors of it? Sometimes it can be easy, like the last digit is 0, then you know in decimal system that 10 is a factor. You don't have to worry too much about it. But if the last digit is not so simple, etc., there are other kind of rules. For example, if the number of digits add up to a multiple of 3, then 3 is a factor. One can remember some of those tricks. But generically, for factors which are not 2 or 3 kind of thing, not something which are small but much larger, there is no easy algorithm. You are reduced to taking a number, performing a division, and seeing whether the remainder is 0 or not. And that is a branching problem because you have to try out lots of number and keep on doing the division. The converse is polynomial. If you are given the factors, all you have to do is multiply and see whether you get the original number or not. And that multiplication is simple, it is polynomial. So this is a kind of problems which are called NP, non-deterministic polynomial. Then what is this stuff? PP. So these are problems which are not solved deterministically but solved only probabilistically. Sometimes you have the answer, sometimes you don't. What is important that the success probability P is greater than half. Okay, so why that half is stuck in? That for simplest situation, just random guessing will give you P equal to half. Because a decision problem, yes or no at the end, don't do any work, just guess it. That already has P equal to half. So you are going to do some work and you should get something more than that. That is why that greater than half is stuck in. And then there is this last bit. Is all the problems where you have only limited space resources, polynomial in the input data, time is unlimited, and whatever you can solve in that particular context is called PSPACE. And this inclusion signs between these various classes gives the hierarchy. This is more complicated than that, this is more complicated than that, etc., etc. The important point to note is that it's an inclusion sign, but with an equality also stuck inside there. And that is a what you call major challenge of this computational complexity analysis, whether it is allowed with an equality or whether it is strictly not equal. Just like something between this and this. And for this statement, nobody knows the answer. And that is what is often called a $1 million questions in computer science, whether you can prove that the equality is ruled out or not. It's a tough problem. And it can be called an accepted wisdom without any proof. Why it is so? Because all you can say is lots of people have tried it with lots of tricks and they have not succeeded in finding an answer. That's about it. And there are prizes announced for this thing, whether you can really tackle this problem or not. It kind of connects it back to this kind of a statement that many times proving the negative sense of the problem is easy, but proving a positive statement is hard. Because here the one counter example is enough. Here you have to solve for many cases and see it works in every case.
So does probabilistic problems also have branches?
This one is strictly greater than. Yeah.
I'm asking if those kind of problems also have branches.
Yeah, it can have branches because it's probabilistic. Probabilistic generally involve the branches all over the place.
If you take the problem into one, then we can explain the equation. Can we say that?
No, it's not that simple. So anyway, this is the hierarchy, and I'm not going to go into any details about it. Accept it. Okay. That this is how things are organized. And now you can ask a variety of questions. Okay. Well, this label NP contains essentially all all the problems which you encounter in various fields of science and technology, they generally all fall into this class NP. Why so? Because of this last bit. You produced an answer. Unless you have a way to verify it, why will you trust it? That is essentially the point. And the verification must be simple enough so they can have an application. So theoretically, all this other stuff is defined, but in practice, problems essentially stop at this particular stage. And there is a extra label which is called NP complete. And the characterization for that is that any NP problem can be reduced to it. Reduction in the sense which I pointed out earlier, that if you solve the reduced problem, you have solved all the other problems. And so in this particular case, it means that if you can solve an NP complete problem, you have solved all NP problems in one go with the same amount of complexity. And then these are, in some sense, the hardest of the problems, because if you solve that, you solve the whole collection. So and there is a well-known example. The problem of a traveling salesman. That you are given and different cities, the salesman has to visit all of them in some round trip, and the problem is to find the shortest of these possibilities. So it's very easy to do a brute force analysis. If there are n cities, the round trip will involve n factorial possibilities. So you start somewhere, you go to any of the other one, then the next one, etc. You don't want to repeat it, any one of them, then come back, whatever it is. There are n factorial possibilities. And factorial is even worse than the exponential in terms of how it grows with n. So if you are going to do any of the search of all the possibilities, it's what you call not a polynomial problem. But how do you find a better solution than just trying out many possibilities out of them? Well, nobody has found an answer. So this NP problem is hard in the sense that the polynomial answer of this searching through this possibility is not known. Of course, you search a large number of possibilities, that is okay, but nobody has found an answer, and it has a branching structure because you start here then you can choose. I want to go here, 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 whatever it is. There are many possibilities. At every future step, you have to have many possibilities you choose. On the other hand, the verification is something which can be made simple, but for that you have to convert it into a decision problem, not the length measured in some distance unit. And that can be done in the language which I described last time. You convert an optimization problem to a decision problem by binary search, and that will allow you to say whether you have a short path or not, whether something else is available or not available. So this is a well-known problem, and it is NP-complete in the sense that if you can solve this, you will have solved all NP problems in one shot, in the sense that every other NP problems can be reduced to this particular problem.
You cannot do verification of NP complete problem.
Yes, for all the verification for anything, including NP complete, is easy. So in practice, lot of effort is actually made to tackle these NP complete problems in various fields, various disguises. Things can be labeled differently, but then you will find some map of one or the other at some particular level. And I will give an example of that, which is much easier to state, and even the verification can be formulated much more easily than this kind of optimization problem. Okay. But now let me go beyond this list. This is all description for the classical logic, in particular the binary language structure which we have used. So then there is this question of extending these labels in the quantum domain. And the first thing which we need is to bring in this probabilistic results from the beginning itself, because the quantum algorithms generically have some measurement at the output which can be only described in a probabilistic language, and then you have to say that this probability is good enough or not. So what is the kind of probability which you are looking at? These are so-called bounded error problems, where the success probability is bigger than 2/3. 2/3 is a typical number which is used. The important point is it is strictly larger than this half. Any number larger than half will do. Instead of 2/3, you want to make it 0.6 or 0.9, it doesn't matter. It is good enough. Why good enough? Because if you are given some success probability which is bigger than 2/3, and then the simple procedure exists that you run the algorithm many times. The decision problem, so you will have large possible answer, and then instead of looking the average probability, which is what this number will give, find the probability or find the result by majority rule of all the answers. Okay. And this probability can be made as close to 1 as possible by, this is instead of multiple I can be more specific, it is polynomial. So it's affordable in that sense. And why so? Well, you can count the success or the failure as probability p and 1 minus p, and then you have to sum up the series, how many times p is greater than 1 minus p and how many times 1 minus p is greater than p. That is the meaning of the majority rule, and it's half of the binomial expansion if you count possibility over a number of trials. What is the sum of half side of binomial expansion? Well, you can take it as close to 1 as possible just by adding up the binomial coefficients. You can work it out rather straightforwardly, and that is essentially why I put this number is 2/3, which is saying that 1 minus p raised to some power goes to 0, faster than 1/2 raised to the same power, much faster actually, and that is why this number is bigger than 2/3. If you want to check this statement, do it as an exercise. It's a very straightforward thing to play around with the binomial coefficient and show that yes, this is indeed possible. All you need is a number which is strictly larger than half. If it is equal to half, this majority rule is not going to help. It is still going to give half and half. So yes, in quantum extension, we'll deal with all problems of this particular type. And there are versions which can define that this P is contained in just at the classical level inside these bounded error problems. No harm done. This was deterministic. Here you added something more. Probability is also allowed, and the probability is bounded, but it is contained in this. And the label for this is a bounded error probabilistic polynomial. One extra letter compared to this. And what is also allowed that from going from classical language to a quantum probability, well, this can only get larger in the sense that If you're not getting any advantage by using all quantum logic, you will just turn it off. And the classical thing is a subset of the quantum logic in a simple sense. So this already is quite obvious. What is interesting or rather unknown is relation between NP and these two labels of bounded error classification. And actually, I can put one more label inside which is also true. This PP is larger for a simple reason that this 2/3 and half are a different game, but it's also interesting that BQP is also inside this probabilistic polynomial. So we have two connections between P and PP. One goes through this NP and one goes through this bounded error problems, but these two separate inclusions, which one is better and which one is not, nobody knows. That whether NP falls before this, after this, no idea. Maybe something which is in here is not in NP, or whether something which is NP is not in here, nobody have any clue. And that is the practical challenge of trying to find problems in this particular class which are not in NP. Okay, so NP problems, you have to find something which is difficult, and BQP will remain polynomial. So then you will have some way to solve a hard problem with polynomial quantum resources. If you can do that, then you have achieved something non-trivial, in the sense that classically the problem was difficult, but you found a easy way to solve it using quantum logic. Because whatever these bounded or problems are, they are all polynomial in some particular sense, and they are therefore easier to tackle than this non-deterministic polynomial problems. And nobody has a remedy or a prescription for doing this. All these years it has been trial and error. People have found examples where the problem is certainly in BQP, you can demonstrate it, and Nobody has found a classical version that is polynomial. The classical version, which is in NP, is known, and then that becomes a very good candidate that yes, this is a place where you have advantage by using quantum logic. That is essentially the game in the whole subject. You can ask that BQP is in some sense easy, is this kind of analog exists that NP complete, any NP problem can be reduced to it. So there is a version and it has a name. More importantly, I can give an example, is labeled by this another acronym, quantum Merlin Arthur, because whoever came up with this name was thinking about certain kind of games which are used as exchange of questions and answers between two parties, and they thought of this what you call British mythology involving Merlin and Arthur exchanging answers and trying to figure out whether something is right or wrong. Okay. But the point is that it is an analog of the NP complete version, which means if you solve this problem, you are able to solve all the quantum problems. Okay. The same way this was true here, that every quantum problem can be reduced to this. Yeah.
Is this one problem or set of problems?
Once you say that every problem can be reduced to it, I can give only one example. Okay, that is enough. There are many equivalent examples you can construct, and the example is so-called Hamiltonian problem, which is very much practical in a physical description. Find the smallest eigenvalue of a given quantum Hamiltonian. That setting is very commonplace. Every evolution of a quantum system will be given in terms of Hamiltonian. Some definition will be there. The job is find the smallest eigenvalue. If you can do that, you solved all quantum problems in one shot, in the sense that it is complete. But of course, it's a hard problem. Nobody has found any answer to it. It's just an illustration of the fact that every other problem can be reduced to this. Something which you can add on to it, that this is a local Hamiltonian, in the sense that physics, the interactions are restricted within certain range. It's not an arbitrary Hamiltonian. Even then, it is a hard problem. Okay. Now some other terminology. which I can also define, and that is a choice of language. At how you state the problem, many times it turns out to be important, and again I will illustrate it by a example, but let me quote first another definition, that there is something called a complement of a particular problem, is just defined by interchanging the output of the decision problem. You can do that by, well, complementing the whole language. Yes or no are going interchanged. One way to repeat this thing is state the problem. So the problem is solved by some example. The complement will be solved by the counter example. You have to flip all the yes or no, true or false, every way where they appear. Okay. And the point is that the original problem and the complement may not have the same complexity, because finding an example and finding a counter example may be different. Okay, so and what is known is for the polynomial class, complement class is the same, but for the NP class, the complement may not be the same, in the sense that finding an answer may be hard, but finding a counter example might be easy. can happen. Okay. So now let me illustrate in a more explicit language about how this phrasing can be used in a straightforward example of just writing some statement.
So in case of polynomial, counter is also having same complexity. In case of polynomial,
Yeah,
counter will also have the same.
complement has the same complexity. So let me write it in a simple language. So let me various phrases, okay? Let me all these kind of descriptions can be very different. What does the first part mean? Just find whether the solution exists or not, without finding the solution at all. Then here says find one solution. But the problem can have many solutions. So you find the total number of solutions. This complement means you have to show that no solution exists. And they are all different phrases, but they actually refer to different problems. And again, one can say that, well, this gradually gets difficult. The complement is actually not so clear. But let me then give a just a very simple situation that the problem is to decide whether the number is prime or factoring the number. When you are asking whether the number is fine, it corresponds to existence of the solution. In the sense it says there is no other factor than the one and the number itself. And factoring will say that if the number is not prime, then there are factors. But you don't know what the factors are. Then the find a solution is actually find the factors. Find the number of solution is find many of these factors, all possible factors, etc. And complement is actually the relation between a prime and factoring itself. in a sense. So what is the status of this? That the problem of deciding whether a number is prime or not is in the polynomial class. This was actually proved not so long back, and important that it was proved by a professor at IIT Kanpur some 20 years back, Manindra Agarwal, and his students. And it was a major breakthrough as far as this number theory stuff is concerned. But this is in NP, finding the factors of a number. It's not polynomial, nobody has found a polynomial algorithm. So these are the kind of situation which arise, and this is just a change of the phrase of what exactly you are looking at, and this finding the number of solutions is even much harder than this language. And it has a different label. It is denoted by this hash sign instead of in front of the P, and all you need to kind of remember that this hash P is actually even worse than the NP in terms of the difficulty involved. But there are all kind of labels which have been invented. The point I wanted to emphasize is phrasing the question is important when we are asking the question of the complexity. We have to look at the words and the sense in which they are used, and then only you can say something. In a colloquial language, these things get mixed up, but this is a hardcore mathematics where things are more complicated. Yeah.
So for the first case, existence of a solution for the prime, it is true. There exists a solution, yes or no. If the number is prime,
The question is either ask, is the number prime?
but a solution
It will be yes or no. If the answer is yes, there are no other factors. The answer is no, there are factors, but you don't know what the factors are.
right, this is the ties to finding those factors.
Yeah. Okay. So this is as much as I want to say about various kind of discussions on complexity, and if you are looking at rigorous computer science, there will be books on the subject. Okay, what I covered in one lecture will have a whole book written on it. So that is too complicated, and I gave a quick summary of what are the main ideas that we will be concerned with as far as this particular course is concerned. And with all this terminology, what I want to do from next class onward is apply it to Boolean logic first. We will have specific problems defined using Boolean logic, and then try to see what are the kind of solutions which we have. And then after that, the exercise of the quantum part will convert those Boolean variables 0 and 1 to qubits. and see what changes by doing so, and whether we have any new ways of tackling the problems. But the first step is to just go through the Boolean logic. This is something which you have seen in a different manner. And again, yeah, I will not go to the examples today, but let me repeat just the definitions. Which I have described before, and different ways of using them, which we will encounter in some ways. So while talking about group theory, I had pointed out that there was this two variable set which is mathematically called a field, and it allows addition and multiplication, and that is all we are going to use. Nothing more than that. But there is a version of this in the logic language, where instead of using these numbers, you use this and or are used, and this one is denoted by symbols. This is a wedge and this is V. And these languages are interchangeable, but they are not the same. Okay. And the problems are ported sometimes in this way, sometimes in this way, and you have to understand these things appropriately. What is the place where this thing differs from this group theory construct is that there is no inverse operation for either of them. Why it is so that if you take a logical AND with 0, you will always get a 0, and you will take a logical OR with 1, you will always get 1. Actually, it should be true and false, but I am using 0 and 1 for shorthand, whatever it is. But these are the operations which say the inverse is not possible, because this is independent. Whatever is here is independent of x, and whatever is here is independent of x. While these things allows inverses. So how they are converted in one to another? Yes, you can do a mapping, but the operations are different. That addition and multiplications are not going to behave the same way as AND and OR. All the other stuff kind of goes through, but this is a difference that you should keep in mind. In particular, there is a distributive law between addition and multiplication, and there is a distributive law between AND and OR that goes through. but still you have to keep the distinction in mind. And I will use most of the time this language, but sometimes I will use this also as necessary. And let me point out one particular simplifying property, that these variables satisfy rather this trivial relation. That means any arbitrary function is a linear function. There are no higher orders which will survive. This is a drastic simplification. So if I take a general function, okay, which will be input to the algorithm, not going to be anything else. Whatever comes as output described by whatever function you want to calculate obeys this linearity property. So you can start by writing some expressions. So how do you know? No, I will stick with just same letter, but we'll put it's a multilinear polynomial. It has to be linear in each variable, because higher orders all disappear. How many such terms you can have? Well, it's not too difficult to count. You can classify the terms by saying that some particular xi either occurs in it or doesn't occur in it. There are only two choices. And you can then list all of the terms one by one, that is x1 included, is x2 included, is x3 included, etc. So this is a multilinear polynomial with 2 raised to n terms. And then the job of the algorithm is nothing but compute all these coefficients. If that is done, you can solve the problem for any arbitrary input. Where is the problem? The problem is that the coefficients are 2 raised to n. So and that is exponential in the input size. It's not polynomial. And so the whole problem comes down to figuring out if the function has some specific property where the number of coefficients are, in some sense, not so large. It cannot be some generic arbitrary function. So the exercise is finding what are the kind of problems where the number of coefficients remains in some sense small. By small means polynomial in n is good enough, exponential in n is not good. And then it is a exercise, generic exercise for arbitrary problems that you want to solve, figure out this particular pattern when you map that problem into binary language. The simplification has occurred by this simple behavior that x square equal to x is good enough. And another simplification which occurs when trying to evaluate this is a linear problem in every variable. So all we need is linear algebra. Don't need anything more complicated. And that is where this course is now going to go. Linear algebra first in the Boolean framework, the linear algebra in the quantum framework. You don't need things which are more complicated than that.